Right, in this video, we're going to talk about the span of a set of vectors. So I'll show you the definition. If S is the set of vectors v1, v2, v3, v4, all the way up to vn, then the span of set S is going to be the set of all vectors x, where we can write x as c1 v1 plus c2 v2 plus some other number of each vector. We can write it as a linear combination of the vectors in S. And so, kind of my translation into English is that the span is the set of all possible linear combinations of these vectors. And if this seems familiar because you just heard about range, well, that's, it is familiar, right? Okay, the range of a matrix is the span of its columns. Okay, I went out of my way to not use that word in the last video, but there you go, there it is. And we're going to kind of lean on that similarity with how we compute the span of a set is we're going to take the vectors in that set, kind of smash it together into a matrix, and then we're going to compute the range of that matrix. All right, so the first example I've got for you is S is 2, 4, and 5, 10. So what we're going to do is we're going to turn S into a matrix and compute the range of that matrix. And hopefully you've got a little bit of experience with that. We're going to subtract 2 copies of row 1 from row 2, okay, 2, and then 0 here, y2 minus 2y1. You've already computed the range of a matrix very similar to this, so I don't think I need to give you a whole lot of detail. We're going to say y2 minus 2y1 equals 0, and so the span of S is the set of all y's in R2 such that y2 equals 2 times y1. Okay, that's a span. And I recognize that wasn't the most interesting situation ever, but let's add a vector to this set. So I'll add in 3 and 6. And you might be saying, well, like, dude, you just added another one that was exactly the same. And that's kind of the point. So if I added another vector that's already, able to be written as a combination of the first two, it shouldn't give me access to any new vectors. So what I would do is I would, go set up the same situation. And I could row reduce, and the exact same thing would happen. I'm going to subtract 2 copies of row 1 from row 2. And we'd see, okay, well, in order for this to not be inconsistent, I need y2 minus 2y1 equal to 0. So again, the span of S is equal to the set of all vectors y, which equals, maybe I could write it differently, y1 and y2 is 2 times y1. That would be a different look for the same set of vectors, right? And okay, so what I'm saying is if I add in this new vector that's actually just, some kind of multiple or combination of the other vectors, it doesn't really change the span. And if you think about if I'd added in a 0 vector to this set, that would not change the span either, because as we saw in the last video, adding a 0 column to a matrix does not change its range. What would change the span is if I added a new vector that wasn't something I could write as a combination of the ones I already had. Okay, so the span of this is going to be, materially different from the span of the other 2 sets that we've looked at so far. So what I'm going to turn the set into a matrix, augment with y1 and y2, and then row reduce. So I'm going to same step, I'm going to subtract 2 copies of the first row from the second row. And then, but I see I've introduced a new pivot. Okay, so I've got 2, 5, and 2. So I've got y1 and y2 minus 2y1. And so I see I'm never going to be able to introduce a row of all zeros into this matrix as I'm reducing. And I've got 2 pivots in 2 rows, so that means that the span, or like if I was thinking about the range of this matrix, it would fill up all of R2. It's 2-dimensional vectors and I've got 2 pivots. But since I'm talking about the span of this set, well, the span of the set is the same as the range of this matrix. So I'm going to say, all right, I've got, I was going to say that the span of S is all of R2. And the last example I've got for you is the span of two three-dimensional vectors. So if I think about all the possible combinations of two three-dimensional vectors, it should be a plane in R3. And if I think about combining these column vectors, I should get a vector with three components back. So okay, the span of S is living in R3, but it's going to be a subset of R3. So I'm going to say, all right, turn it into a matrix. And maybe it's like, oh, okay, well, I can't really do anything with this first column because it's already cleared out. So maybe I should try to introduce a pivot into the second column. Okay, maybe I'll use that 2, right? I could use that to clear out that 1 and that 4, but I'm going to just use it to clear out the 4, right? Because this already has a pivot in it. It's not really going to be, not something I can do much with. I'm not going to be able to introduce a 0 row, especially in that one. Okay, so 1, 1, y1, 0, 2, y2. That's also a pivot, so that row is not telling me much about the range. And then down here, if I subtract 2 copies of row 2 from row 3, I'd get y3 minus 2y2. I should have been committed to the right edge of my matrix so early. And now I'm going to say, okay, I've got my row of all zeros. That's where the conditions come from. y3 minus 2y2 equals 0, and y1 can equal whatever it wants. This is a plane. This is like z equals 2y. You could write it like that, or we could say that the span of S is the set of all vectors y such that y3 minus 2y2 equals 0. Now, I think, in retrospect, I kind of wish I would have said, okay, y, which is in R3, just to make sure think there was any other components that could be whatever they wanted besides y1. Okay, but that's, I think this is going to be another, I'm not trying to make these videos too long. I just want to show you what it is, how you compute it, and then set you loose to compute a bunch yourself. So that's going to be all for this one. Thanks for watching.